Cuesta College, Math 265A, Calculus 1. I'm Joe Vasta, and we are going to cover 4.4. And the thing about 4.4 is we've already covered a lot of this stuff in 4.3. We are graphing functions in problems 13 and 15 through 22. You're going to be looking at polynomials, and the rest that I assigned, they'll be root functions. We are going to avoid graphs that have the asymptotes on them, and let's see what we want to look for when we graph functions. We want to find the domain, the intercepts, symmetry, take the first and second derivatives, look at increasing, decreasing, local maxes and mins, concavity, inflection points, and then graph the graph. So we're going to do that with a few problems, and then we will be done with this section. So we pretty much know all these things here. We've seen them all before. We're going to go ahead and look at our first problem here. Our first problem is this one here that says f of x equals 2x cubed minus 3x squared minus 12x. And this here is a polynomial. So if they asked for the domain, the domain happens to be anything. You can put any real number in there. And I'll put my domain in interval notation. So there's the domain. Okay, the next thing that I want to take a look at is my intercepts. Now with my intercepts, I'm going to be looking at, we'll rewrite this function so it says y equals 2x cubed minus 3x squared minus 12x. We'll go for the y-intercept first. The y-intercept is gotten by setting x equal to 0. So it looks like I get 0 on the right hand side. I do not want to write my y-intercept as y equals 0 because that's the equation of a horizontal line. I want to do one of two things. I could either say it's 0, 0. And another acceptable answer in this class, if I said what's the y-intercept, you could just say that it's 0. Okay, we're still doing intercepts, and I have to find my x-intercept. To find my x-intercept, I set y equal to 0. So that's what I'm going to do. 0 equals 2x cubed minus 3x squared minus 12x. I like to have this stuff on the left-hand side, so I'll put it there. 2x cubed minus 3x squared minus 12x. This equals 0. I'm going to factor out an x, and so when I do that, I end up getting an x times a quadratic here. And the hope would be that this quadratic can factor over the rational numbers, so I'll go 2 times 12 is 24. Are there factors of 24 that subtract to give me 3? So let's see. 2, 12, 3, 8, 4, 6. None of them have a difference of 3, so this is rather sad because on this thing I have to use the quadratic formula. So I know when I set this thing equal to 0, I'm going to get x equals 0. X equals 0. And I'm setting this guy equal to 0. I cannot factor it over the rational numbers, so the quadratic formula is what I'm going to do. So negative b plus or minus the square root of b squared minus 4 times a times c, and then this is all over 2 times a. Looks like I'm going to need another piece of paper here. Okay, so for this, I'm going to have x equals 3 plus or minus the square root of 9, and I did mess up here when I plugged that into the quadratic formula. This was 4 times a times c minus 4ac. C is negative 12. Okay, so let's see. 4 times 2 is 8. 8 times 12, I believe it's like 96. So I have plus 96. This is all over 4. And what do I have here? I have, this page wants to keep coming up. Oh well, it is what it is. I have 3 plus or minus the square root of 105, which I believe that cannot be simplified, and then this is all over 4. So my x-intercepts, there are 2 of them, and there they are, my x-intercepts. I could say 3 plus root 105 over 4, comma 0. And then I have 3 minus square root 105 over 4, 0, and I get 2 of them from that. And then don't forget that we have another x-intercept right here, which is 0, 0. We're not so surprised because that was a y-intercept. So here are my x-intercepts. It's acceptable in this class to write them like this, you know, to just write the values here. 105 all over 4, and there's 2 of them, and then there's the third one, so that's acceptable as well. Now I went ahead and plugged those into the calculator, so just in case, you know, we do have to graph these. This guy right here is about 3.3, and this guy right here is about negative 1.8. And so that completes the intercepts. So far we have not done any calculus on this problem. We've just been doing pre-calculus skills. Because we are moving the paper up, let me just remind you what the function is. F of x equals 2x cubed minus 3x squared minus 12x. So that's what we're doing. Now, symmetry. So that's the next thing on my list here. That's symmetry. And really, if you forget to do this, this is all right. But when your graph does have symmetry, you really only have to graph half of your graph and do calculus on only half of it, because the other half you get for free. You just kind of mirror it through the y-axis or rotate it 180 degrees through the origin. And so, you know, if you want to skip that, that's all right. I'm going to go ahead and just show you, in case you're wondering, well, how do you check for symmetry? So here's symmetry. You go ahead and you put negative x in for x. Okay, so that's what usually we feed these functions like f of 5, 2 times 5 cubed, etc. But now it's f of negative x. So that's what I'm going to do. This is my test for symmetry. Maybe you remember this from pre-calculus, and maybe you don't. It doesn't. We forget things. And so what this gives me is, negative x times negative x times negative x is negative x cubed. Okay, so the negative's not going away because that's odd, so this is negative 2x cubed. And then we have negative x times negative x is positive x squared, but there's a negative 3 there, so we have minus 3x squared, and then over here we have plus 12x. Okay, so what is this test? This test says you put the negative x in and you see if you get the same function. Do we get exactly f of x here? No, it is not f of x, so which means it is not an even function, that means it does not have y-axis symmetry. So this does not equal f of x. So that means there's no y-axis symmetry. Or we can say that it is not even. Now, does this equal negative f of x? It almost does. Negative f of x would be, each of these things is negated. So you would have a negative, this guy would be negative 2x to the third plus a 3x squared, and we don't have that. So the first one we do have, but I mean, it has to be, everything has to be negative. So this does not equal negative f of x, which means there is no origin symmetry, which means that the function is not odd. What does this mean here? This means that there is no symmetry. We've wasted a lot of time here doing this. This right here was just a waste of time. If you're watching math on YouTube, then you already knew you were going to be wasting some time. Let's go ahead and do some other things. Okay, so there's no symmetry, but when there is, that helps out. First and second derivatives. Okay. So, another piece of paper. We want to go ahead and look at some derivatives here. Let's go ahead and rewrite this function here. F of x equals 2x cubed minus 3x squared minus 12x. And we'll move on. So we'll know that we found the intercepts. The domain's all real numbers. We pretty much have that. I'm going to go ahead and take some derivatives. The first derivative happens to be, we're just using the power rule here of derivatives. So 6x squared, and we have minus 6x, and then we have minus 12. And the second derivative, we're going to be using both of these things. This gives us 12x minus 6. Okay, now I don't have it on the list here, so here is my original list. But in your book, they're going to ask you for the critical numbers. Your book will say the critical points, and then they'll also say the candidates for inflection points. So we'll find all that, and we'll write things down as we find them. I'm going to go ahead and put a box around the first and second derivative so we don't lose it. Let's go ahead and find the critical numbers, or as your book likes to call them, the critical points, but they usually just write them as numbers. How do I find the critical numbers? I set the first derivative equal to 0, and I solve. Critical numbers are found by setting the first derivative equal to 0, and if there is a denominator that has x's, you set the bottom equal to 0. You find the places where the derivative is 0 or where it does not exist. So I have to solve this quadratic equation. Hopefully I do not have to do the quadratic formula again, but if I do, then I will just be shutting the video off, and I'll just quit my job. That's what I'll say. No more quadratic formula. So we have x squared minus x minus 2 is 0. Factors of 2 that subtract can give you a 1. Oh, great. So this is going to work out. Now, if we did the quadratic formula, that would also work out as well. So when I do this, I end up getting, let's see, 1, 2. I want the 2 to be negative and the 1 to be positive. I set each of those things equal to 0. I end up getting negative 1, positive 2. So if your book says, hey, what are the critical numbers, or critical points, you can say negative 1, 2. Now, what do we do with these critical numbers? Why are we even finding them? It's going to help us answer the questions where the graph is increasing and decreasing, and it will also help us find local mins and maxes if it has any. So let's move this up a little. And what I do, I'm going to do the first derivative test we could do the second derivative test. I like the first one better, but there is a time and place for a second derivative test. And you might see me do that in the next section, 4.5, when we do optimization. Let's go ahead and draw a number line. It's kind of important that we know we should always label our number line. This number line is going to have f prime on it. And I'm going to put my critical numbers on there in the correct order. And I'm going to find like where things are negatives and positives. So how do I do that? I pick a test point from like the first region, from negative infinity to negative 1. Perhaps I'll pick negative 3. Okay, so negative 3 is like right here, or here, I don't know where it is, it's somewhere in here. And I'm going to put it into the derivative. Now, when I put it into the derivative, I could, instead of dividing by 6, I could have had a 6 right out here and factored out the 6. But you want to take note that this guy right here is the same as the derivative, okay? Well, really all I'm looking for is the sign, if it's plus or minus. And so when I put negative 3 in here, I end up getting 6 times negative something. So positive, negative, negative. Okay, so, you could say positive, negative, negative, which gives me a positive. Now, so for those of you who are not as lazy, you can put the negative 3 right in to this derivative here, and you would end up getting, 9 times 6, so you'd say 54 plus 18 minus 12, and you'd get some positive number. And it's pathetic. I'm too lazy to even say what that is. But I want to stress the point that it doesn't matter. You just put a plus there. And this would have been the case if you had put f of negative 100 in, it would have been plus. So this tells us that the slope is positive, which means from negative infinity to negative 1, the graph is going up. Okay? Now, it might be that this guy is going to end up being a local max, but we don't know. We have to do some other tests here. So we can do a number in the next region, which was probably a good number is 0. And we only care about like the plus or minus. You can even go back up to the original derivative there and see that it's going to be a negative 12. So you know it's going to be negative. So, oh yeah, look, our graph goes up and then at negative 1 goes down, which means this guy is going to be a local, let's see if it goes up and then down, a local max. And actually we'll write it all out officially pretty soon. Let's go ahead and pick a number that is on the other side of 2, like 5. And we can put it into the original derivative, or, if I put it right here, I have a plus. 6 is always plus there. And then we have plus, and then plus. It's 3 pluses in a row multiplied by each other. That gives us a plus. So looks like the graph goes down and then goes back up, which shows us that we will have a local minimum at 2. So in our list of things that they asked us to do, they asked us to find our where it's increasing and decreasing and our local mins and maxes. So if we want to officially write that out, we can use this to help us. So f is increasing and f is decreasing. Okay, so officially it's increasing from, these are x values, from negative infinity to negative 1. We're not going to put the union, we always list our increasing, decreasing intervals. And then from 2 to infinity. Your graph is decreasing from negative 1 to 2. Negative 1 to 2. And so there it is. If they ask increasing, decreasing, that's like how we like to answer it. Another thing they asked in our list of long things happens to be local mins and local maxes. Okay, so there is a local max. It's at -1. But if we wanted the local maximum point, this would be -1, comma. Now how would we get the other value? Okay, well let's come back to that. Let's write up our local min. Local min, we saw from this diagram, is at x equals 2. And then there's a y coordinate. So lots of times what people will do, you know, when they're just like scrambling to figure things out, is they would go, oh, let's go ahead and put the -1 back up into the derivative. Well, if you do that, you're going to end up getting 6 plus 6 minus 12. You're going to get a 0 there, and that's not how you find the altitude or the height of where the local max is. You actually put the -1 into the original function. And so that's going to give us a -2 and a -3 and a +12. So I would say that that's about 7. And you're going to do the same thing with 2. You put it back into the original function. And I've already done the calculations on this. And I was going to lie and say, oh yeah, and pretend like I was doing it in my head. But -20 is what I got for that. So that happens to be the local min and the local max. Okay, so now the next thing on our list happened to be concavity. And concavity is gotten by the second derivative. Increasing, decreasing is gotten by the first derivative. So before I find the concavity, I have to find something called, not the critical numbers, but the candidates for inflection points. Okay, so that's what I'm going to find, the candidates for inflection points. Maybe I'll underline this. And how do I find the candidates for inflection points? I take the second derivative and I set it equal to 0. Okay, so this is it looks very familiar, because that's how I find the critical numbers, which are really candidates for local mins and maxes. I take the first derivative and set it equal to 0. So here's the second derivative written right here. So when I do this, I go ahead and, let's see, 12x equals 6x equals 1/2. Okay, so that's kind of a bummer. You know, it's a fraction, but oh well, we're just going to deal with that, aren't we? The candidates for inflection points. So if they asked, you know, hey, what are the candidates for inflection points? You would say 1/2. Now I'm going to go put those candidates for inflection points on a number line. And I want to label this number line correctly, so I'm going to label it F double prime. And I'm going to put my candidates on the number line, so this is 1/2 right here. And I'm going to do the same thing with the pluses and minuses, but I'm going to be checking not with the first derivative, but with the second derivative. So give me a point that's in the first region. A lot of people would say, well, 0 is on the number line, and that would be pretty good. So I'm going to go ahead and, oh, okay, so here is something that I realized that I did. And when I had this right here, that was bad. That was very bad. When I'm plugging them into the a function here, what I plugged in for, these were for the local mins and maxes, I was plugging this in to the derivative. So the people who are just looking at the PDFs will never know that I messed up. Back to this. Once again, some teachers are taking the approach, they're gonna edit their videos, and if they make a mistake, they're gonna redo their videos. I would not be able to crank out all the videos if I did that. So I'm going to plug like a number like 0 into the second derivative. And what I end up getting here, where's the second derivative? I think I have it right there. I end up getting a negative. Now this is telling me something when it's F double prime. This is telling me that it's concave down. Okay, so this is a negative there. Okay. I'm going to plug a number into the second derivative to the right, maybe a 1. And let's see, I end up getting, you know, +6. All I care about is the positive. And so I have plus right here. So we find out that when you switch concavity, that 1/2 actually, even though he was a candidate for an inflection point, he wins the election. He is an inflection point. So on the list of things that we had to do, we have to do concavity. So let me go ahead, and I have lots of pieces of paper here. That is the concavity. I'm pretty sure that I wrote my increasing, decreasing. Okay, well, I'm just going to trust the fact that that's what I did. Oh yeah, here it is right here. I was looking for that. Okay, so, wow, this is a good day. Let's go ahead and say that it is concave up on the interval. So F is so this is F. F is increasing, decreasing. F is concave up from 1/2 to infinity. So from 1/2 to infinity. And F is concave down, Y the frown, from negative infinity to 1/2. Okay, so from negative infinity to 1/2. And so that's our concavity. So they say, hey, describe the concavity. We just did. If they ask us for inflection points, okay, so I'll spell it out here. Inflection points. Well, there's only one inflection point, and it's at 1/2. And how do I find the y coordinate of that? I don't put the 1/2 into the second derivative. I end up putting the 1/2 into the original function. So there's the original function there, and what an ugly thing to do. Okay, it's terrible. So when I went ahead and did this, I ended up getting negative 13/2, or you can write that as negative 6.5. We can do that. We didn't round, so that is an exact answer. There's my inflection points. Okay, so now we come to the part where we have to graph this. And what I want to do, I know this is pretty messy in here, is I need another piece of paper. I'm going to try to put these number lines. Maybe this will work here. Yeah, I think I'll do this. I'm going to go like this. I have to put those number lines sort of right next to each other. And I'm going to draw a new number line right over here. Okay, so let me go ahead and do this. So I got a new number line, and I have -1, then I have 1/2, then I have 2. Okay, so this number line, and this is just the way that I do it. Books are going to do these things differently. I'm going to need to get a red pen and a blue pen. My blue pen means increasing. So this is talking about increasing, decreasing. So increasing, I'm going to make the number line blue. Sometimes I'll choose green, so it's blue this time. It's increasing from negative infinity to -1. It's also increasing from 2 to infinity. So let's just go like that with the blue. Okay, decreasing I'm going to represent in red, and it's decreasing. I'm going to make sure that we're capturing all this on video. Okay, it's decreasing from -1 to 2. So let's go ahead and do that. Okay, in terms of my concavity, there's actually 4 different things you can put above each of those regions, you know, and I'll write out the 4 things. You know, you can go like this. That's decreasing concave up, decreasing concave down, increasing concave up, increasing concave down. Okay, those are the 4 things, okay? So let's go ahead and do this. This is increasing, and it's concave down all the way to 1/2. So sorry, did I say increasing? Yes, it is. It's increasing concave down. So increasing, meaning we're going up and it's concave down, so I'm going to write something that looks like that. Now, this red part reminds me that I'm now, the graph is going down, it's decreasing, but I'm still concave down, which is the curvature toward the ground, concave down by the frown, so I'm going to go like that. I'm still decreasing, but from 1/2 on, I'm concave up, so I'm decreasing concave up, and then from 2 to infinity, I am increasing, that's what the blue stands for, and I'm still concave up, so increasing concave up goes like that. Wow. Okay. We also know that this guy right here is a local max, and it is at -1, 7. And we know that this one is a local min. So I'm summarizing everything that I found. Local min at 2, -20. And the inflection point is at 1/2, -6.5. Of course, I have intercepts and all that other stuff. So let's go ahead and graph this. Okay, so I don't think I need, well, who knows what I need. That's going to help me graph this. I'm going to put the y-axis right here, maybe. I don't know. It's not going to be perfect, but we're going to try to do the best that we could. And then we'll go like this. Put the x-axis right here. So here's x, here's y. We've got -1. And we have 1/2 there, and then we have 1. I mean, it's not perfect. See, look at this. I'm already messing this thing up. And then we have 2. And so here is 1/2 right here. We'll go like that. There's 1/2. Okay, I'm going to go ahead and put a local max at -1,7. The scaling on my y-axis is going to be different, so I'll put that's 7 up, because I know I have to go 20 down for that one. In fact, let's do that. 2, -20. We'll go down right here. And then we have an inflection point at 1/2, 6.5. So 1/2, 6.5 is right there. And, you know, I'll just go ahead and make some nice points there. And so now I'm going to use this as my guide. You know, as I come from -infinity, this graph is increasing and it is concave down. And then here's a max, and it's still concave down all the way to this inflection point. So let's see if I can actually draw that. Oh, we also, one other thing we do have to worry about is I found some intercepts like a long time ago. I don't even know where they are. They're lost. Oh, here they are. Okay, so I have an intercept. I have an X and Y intercept there, and then I have some other X intercepts. You know, one at 3.3 and one at -1.8. Okay, so we'll just keep that in mind here. So this kind of comes down, still concave down, and then this one's going to come down right here, and we go like that. So, you know, it's not going to be perfect, but I believe that this point right here is -1.8. Let's label all these things. This is -1,7. I'm not going to label the origin. That's the one time you don't really have to label the x-intercept. And I'll label this after I'm done drawing. Okay, so there's concave, concave down, y the frown, because we're doing calculus. And now the rest is going to be concave up. And so between 1/2 and 2, I'm decreasing, and then after 2, I'm increasing. So it's going to look something like this. And then it's going to come up like this. And maybe it would have been wise to actually put this on the x-axis, but if you look at your other x-intercept, I said it was approximately 3.3. The min is 2, -20. And then we have this guy right here, which is 1/2. And I'm kind of, here's a fraction and here's a decimal, so that's bad practice, I guess. -6.5. And so those are all the important points. What your book is going to do is they're going to say, oh, this guy right here is an x-intercept. You know, this might be too blurry on the on the YouTube. And then this right here is a local max. This guy right here, this is an X-Intercept, X-Intercept, and Y-Intercept. This right here is an inflection point. I'll abbreviate IP. This is a local min. And then we have an X-Intercept here. I'll just put it right below, X-Intercept. And there's the beautiful picture. And you may have remembered in pre-calculus, maybe if you took it at Cuesta College, you learned how to graph the polynomials, but you were also told that we don't know how to find these mins and maxes in pre-calculus because we never had a derivative gun. And now that we know about derivatives, not only can we find the mins and maxes and know where the graph is going up and down, but we can also plot its concavity, and when things are concave down, and then it switches to concave up at that point. So this gives us a nice, I don't know if I should say beautiful, but it is. It's a beautiful graph of a polynomial, and we'll actually show you, maybe in the next section we'll have some polynomials, and it will describe some real world situations, and in those optimization problems we're trying to find either the max or the min. So we're going to see, you know, right now this seems kind of like a dumb skill to have, but when it comes to the business world and you're trying to maximize your profits and you've got a function that looks like this that has a local max, it's not going to be such a dumb thing to know how to do this. So there it is. That is the graph of the first one. It only took us like 36 minutes. Let's go ahead and do another problem. And let's go do problem number 2. You know what we're going to do on problem number 2? We're going to do the same thing. We are going to find the domain. So I'm trying to fold this so we can see this here. So I'm going to get rid of this. There's this right here. And that's what we're trying to find. We're trying to find the domain, the intercepts, symmetry, all that other stuff. I'll kind of move this list out of the way, and we'll see if we can get this problem done. And then ultimately we'll graph it. And oops, I just bumped the tripod. Okay, I think it's good enough. So the first thing that we want to do when we do these problems, perhaps, is we want to say, hey, what is the domain? The domain, well, the deal is, for the domain, it's not going to be all real numbers, because there are going to be some instances where you have negatives under the square roots, and I know those are imaginary numbers, but we're graphing on a, you know, real rectangular system. So basically, to find the domain, you got to say that this right here, the argument of the square root, has to be greater than or equal to 0. So you might think back to your pre-calculus days, how do I solve a polynomial inequality? You factor the left-hand side, 5 minus x, 5 plus x. This is greater than or equal to 0. You find the zeros of that. So this is, you know, because this function right here, I mean, it's not our function f here, but you find the zeros and they are 5 and -5, and you go ahead and you put those on a number line. Now we're not doing critical points or anything like that. We are just trying to find the domain of this. And then you do some test values, like if x is 0, you have a positive times a positive, so this is positive. And if x is 27, you have a negative 5 minus 27 and 5 plus 27, so that's negative. And then if x is negative 10, you have 5 minus a negative 10, so you get a positive and a negative 10. Yeah, so that's going to be a negative. Positive times a negative is a negative. Wow. So when is this thing greater than or equal to 0? Here's the zeros here. It's going to be greater than or equal to 0 from -5 to 5. So -5 to 5, including those endpoints, because you could put 5 in here and you can take the square root of 0, which is 0. So there's the domain, which is kind of crazy. This thing's not going off to infinity. When you go to the right or to the left, it's somehow going to stop. And so this is a root function. Let's go ahead and do the next thing on our list, which would be the intercepts. So I'm going to go ahead and find the Y-intercept. To find the Y-intercept, I set x equal to 0. And you know, if you like, your function can be written like this. The negative sign's going crazy there. So to find the Y-intercept, I set x equal to 0, and I get 0 times the square root of 25, and it doesn't really matter what the square root of 25 is because this is 0, so the Y-intercept is 0, 0. It's not always going to happen that way. I guess I just picked some examples where it did. The X-intercept. Oh, let me go back to the other problem. You notice how I said X-intercept and there were more than one of them? There. Okay. Plural my intercepts on that one. Okay, so how do I find the X-intercept? I set y equal to 0. Okay, so let's do that. 0 equals x times the square root of 25 minus x squared. Okay, so let me go ahead and switch sides here. 25 minus x squared. And this equals 0. So it looks like x equals 0. And so does this piece of junk right here. Okay, with that piece of junk, I'm going to square both sides. And that gets rid of the square root, so I have 25 minus x squared equals 0. 25 equals x squared, or we could say that x squared equals 25. I'm going to do the square root property, which gives me x equals plus or minus the square root of 25 plus or minus 5. So it looks like this one has to be pluraled as well. And my x-intercepts, there's 3 of them. 0, 0, 5, 0, and negative 5, 0. And so that's good to know what your intercepts are when you're graphing a graph. Let's go ahead and do the next thing on our list. The next thing on our list happens to be, can we find if this thing has symmetry? Now, this might be something you say, I'm going to skip, and you can. You can skip ahead if you don't want to do this symmetry part. So, is there symmetry? And my original function looks like this. I am being redundant here because you can only fit so much in the camera. Okay, so we have that right there. I'm going to plug a negative x in, and I end up getting negative x, and then we have the square root of 25 minus negative x squared. So this is negative x, and then this is really 25. That minus is still there, and then you have negative x times negative x, which is positive x squared. The question is, did I get exactly the same function? And the answer is no, because there's like a negative here. And did I get minus our original function? And the answer is yes, we did. This is minus f of x, which means our function has origin symmetry, which means sometimes people call this an odd function. Okay, so this is what they call it. So we have an odd function, which really means we only have to graph half of it. Now, what will happen is I'll probably forget to do that, and then I'll just graph the full thing, and you know, we could then come back and go, oh, we only needed to graph half of it. But this is good to know. At the end, when we look at our graph, we'll see the origin symmetry. So our next thing that we want to do is, I'm going to try to keep track of these pieces of paper so I don't lose them like I did last time, is I want to get the first and second derivative. Okay, so our function looks like this. It looks like x times 25 minus x squared to the 1/2 power. So let's go ahead and find the first derivative. This is going to be fun. Okay, the first derivative, you're going to use a little product rule here because you have the x times that. So the derivative of the first times the second. And then I have plus the first times the derivative of the second, so I'm going to be doing some chain rule here. So I have something to the 1/2 is going to be 1/2 something to the negative 1/2 power, and then I'm going to take the derivative of the inside, which is going to be negative 2x. Okay, now what I want to do is simplify this first derivative. The 2's are going to cancel there. And what I end up having here is the square root 25 minus x squared. And then over here I have plus, what do I have? I have x, and then that guy's going downstairs. As the 1/2 power, I'm going to actually write it as the square root of 25 minus x squared. Another piece of paper. Good thing Questa is supplying all this paper here, because I don't think I can afford it. Okay, and also it's a good thing it's not a run on regular copy paper. You know, people are still going crazy over toilet paper, but they haven't realized that this paper right here works just as good as toilet paper. And you're like, well, doesn't that make you a little sore? No, what you got to do is you got to put some warm water on it, and then it gets all like soft, and then it works just as good as toilet paper. Don't press too hard because it tears easy. So there it is. Now, because I put that out on YouTube, I've just created another thing that we're going to have shortages of, which would be copy paper. And you'll go visit a friend's house after this shelter in place, and on the top of the toilet they'll have a whole stack of, they'll have this. There'll be no toilet paper, and it will be, what is this, Pro Red, or what is Pro Red printed paper, best for black and white printing and wiping. Okay, so that's, we can change that. Engineered to prevent jamming. I'm gonna stop doing this. Okay, so yeah, we don't want to have any paper jams if you are going to be using that. Let's go ahead and continue here. What does this guy need? This guy right here needs a, I'm going to go ahead and get rid of this equal sign. You're like, why get rid of the equal sign? So I can put it over here. That's kind of awkward to do. And so I could multiply top and bottom by the square root of 25 minus x squared, and then over here we have the square root of 25 minus x squared. Okay, so what does this give me? It gives me, the square roots go away, and you just have 25 minus x squared. And there's something else that I forgot to do. You know, here I was talking about the toilet paper, and of course that's me being incompetent. I have an x here, and I know all the good students were just like, what is wrong with you? There's lots of things wrong with me, but one of them was I missed this times the x there, which gives me an x squared on the top. Okay, so go figure. And then also, look at this. Another thing I missed was this right here, this negative. So how do I turn that into a negative? I use this right here. How do you like that for this whiteout? Look at that, I didn't have to do anything else. So it looks like I have minus x squared all over this right here, 25 minus x squared. Actually, it's a little too late to change calculus teachers. Telling you right now, you could have had pretty much the pick of calculus teachers. You could have had so many better teachers than this guy who makes mistakes, but you're stuck. I know you can turn off the video anytime, so maybe that's what you're going to do. What does this thing become? This thing becomes 25 minus 2x squared. This is all over the square root of 25 minus x squared. Okay, so that right there is the first derivative. And the sad part is we want to do more. We want to compute the second derivative. So for the next 25 minutes on this video, maybe I'm exaggerating, I'm going to compute the second derivative, and then we'll come back and make the connections with mins and maxes and concavity. So when I do the second derivative, I probably want to write the first derivative. It can be written, you know, like this, but it could also be written with a 1/2 power on the bottom. So I'm going to go back to that. And this is going to be a mess. I'm going to get my Pro Red printer paper all messy. So I know that sounds bad, but it's going to be messy, full of messy math, not what you might be thinking. Okay, so I'm hesitating here. I'm thinking to myself, why did I pick this problem? It's not that bad of a problem. The algebra is going to be a little bad. I'm going to take the derivative, I'm going to zap this with the derivative gun and do the quotient rule. Okay, the quotient rule says the derivative of the top. Okay, so that's 0 minus 4x, so negative 4x. That's the derivative of the top, times the bottom, minus, because that's part of the quotient rule, and I'll try not to forget that minus when I'm going to the next line, minus the top times the derivative of the bottom. The derivative of the bottom is going to be a chain rule. We're going to go 1/2 25 minus x squared to the negative 1/2 power. And then we're doing a little chain rule. So the chain rule says we go negative 2x. So if you're sitting there going, what just happened? Okay, let me go ahead and circle things here. So we have that. I don't know why I'm using the orange highlighter, but it's too late now. We've already... So there's the derivative of the top times the bottom minus the top times the derivative of the bottom, all over the bottom squared. So this is 25 minus x squared to the 1/2 squared. Okay, so right away on the bottom we can see that when we square that, you're just going to have a 25 minus x squared on the bottom. Okay, now on the top, going to look a little different. Okay, so we're going to have negative 4x, 25 minus x squared to the 1/2. Okay, so what do we have here? We have 25 minus 2x squared, which is not the same as that, so that's a bummer. Okay, so let's go ahead and not forget a few things here. Okay, the 2's cancel, and then I have 2 minuses, which will give me a plus. Okay, that guy's getting sucked down to the bottom, not here. I mean, we're just going to have a bottom of this, and then this guy's staying where he is. So this is 25 minus 2x squared, and on the bottom of this part here we have 25 minus x squared to the 1/2 power. This is all over 25 minus x squared. Okay, once again, I'm getting mileage off of this here. Okay, this equals that. So what I want to do is I want to get a common denominator for the things on the top, and that common denominator is going to be this, the 25 minus x squared to the 1/2 power. This is 25 minus x squared to the 1/2 power, and then I have it up here too, so I better put parentheses around there. 25 minus x squared to the 1/2 power. What a mess this looks like. Okay, the next step here, I actually have two of these things here. So I have this guy right here to the 1/2 power, and then this guy right here. Look what happened. It got smeared. Okay, you got something. This thing's trailing now. Look at it. We can trail marks on my Pro Red printer paper. Scary. Okay, so look at that. So we have 1/2, 1/2. It's just going to turn into a 25 minus x squared. So I have negative 4x, 25 minus x squared. Okay. Then I have plus 25 minus 2x squared. This is all over 25 minus x squared to the 1/2, which is all over, running out of room on this paper. 25 minus x squared. And then, of course, this is all over 1. And so there's the longest fraction bars right there. Another piece of paper. Okay, so on the top, I'm going to go ahead and distribute that negative 4x. So we have negative 100. Yeah, it's going to be negative 100x plus 4x cubed. And then I have a plus 25. And this is going to be minus, let's see here, making sure I do everything correctly, minus 2x squared there. Okay, so, and I'm making sure that things are looking good. Yeah, unfortunately I do not know how to multiply through here. Let's try this again. This is a negative 100x. Or maybe I do. And then 25, and then that's a squared there. Now, what I'm also going to do, and at any time you see a mistake, just bang on your monitor or screen, and I'll answer that question. Let's continue with this. Making sure that I'm doing everything right here. Okay, so now I'm coming back down here. Maybe I really should redo this video. I did the same exact thing that I did before. You're like, what did you do, Joe? I forgot about this x right here. Okay? Because I forgot about that x, it would have been 25x minus 2x cubed. Man, the same mistake. So I should have probably got more sleep. And so this right here is the 25x minus 2x cubed. And then this is 25x minus 2x cubed. Shame on me. Okay, so now come back over here. I will not redo the video. This is going to stay this way, and people are going to go, oh, that Vasta, he doesn't know how to do math. Well, that's quite all right. So look what we have here. We're going to do a copy dot flip, and so I'm copying the top. It's like the same thing. Every time I take a derivative, I'm doing exactly the same mistake. I feel like Homer Simpson. And so I'm going to flip that right there. There's the copy dot and then flip. So this is going to be 1 over 25 minus x squared. Right there. And so on the top, I end up getting 2x cubed minus 75x, and on the bottom I end up getting 25 minus x squared. The camera just ran out of something, I don't know, so we started it up again. 25 minus x squared, and then we have a 1/2 power and a 1 power, so this is going to be the 3/2 power. And so, to make things just a little nicer, I can factor out of the top maybe an x. You really don't need to do that. We have 2x squared minus 75. This is all over 25 minus x squared to the 3/2 power. We even probably forgot what we were doing, maybe. I don't know if we forgot what we were doing. Let me just remind you of what we were doing, or what we're doing. So we're trying to figure out how to graph this function here, which looks like x times the square root of 25 minus x squared. We found the intercepts, one y-intercept of 0, 0, 3 x-intercepts at 0, 5, and -5. We found that there was some symmetry with respect to the origin. And then we also found that, hey, you know what, the first derivative happens to be this right here. It happens to be 25, or no, how did we do it? We went 25 minus 2x squared all over the square root of 25 minus x squared. And the second derivative, that's what we have written right there, is x, and then we have 2x squared minus 75 on the top, and then we have 25 minus x squared to the 3/2 power. So that's what we've done. We've computed some derivatives, and now I want to check for critical numbers. And to check for critical numbers, I'm going to look at the first derivative. I'm going to set the top equal to 0. And so when I set the top equal to 0, I end up getting what? 25 minus 2x squared equals 0. I'm going to set the bottom equal to 0, and when I set the bottom equal to 0, 25 minus x squared equals 0. This one's going to give me two x values. X equals plus or minus 5. Now if you look at the domain, and that was the first thing we found, that plus and minus 5 are actually non-interior points. So these guys right here are not critical numbers, and so we're just going to leave those alone. The one that we're interested in is this right here. So 25 equals 2x squared. X squared equals 25 over 2. 25 over 2 happens to be, what is it? This is 12.5. So let's just write that. X squared equals the square root of 12. Oops, not. Why did I put this? Okay. So there it goes. Equals 12.5. And so x equals, from the square root property, plus or minus the square root of 12.5. Okay, and if you wanted to know an approximation for that, I approximated those, and this gives me plus or minus about 3.5. Okay. So let's go ahead and put these guys, another piece of paper. Let's put our critical numbers. There's two of them. So, I mean, if they ask what are the critical numbers, you can say they are 3.5 and negative 3.5. We're going to go ahead and put them on a number line, the number line being labeled F prime. Here is 3.5, negative 3.5, and then here is 3.5. And of course, we can't have anything beyond 5 and beyond negative 5. So we're just graphing this thing between negative 5 and 5. That's what the domain says. I'm going to go ahead and plug a 0 into the derivative. If I plug a 0 into the derivative, so this is f prime of 0, I end up getting positive on the top, positive on the bottom. This gives me positive. So looks like the graph is increasing there. If I put like 4 into this thing right here, you're going to get 4 squared, which is 16 times 2, which is 32. 25 minus 32 is negative on the top, and then it's positive on the bottom. You're going to get that. And you can go ahead and, so I just went ahead and plugged 4 into the derivative and realized it's going to be negative. And likewise, if I put negative 4 in there, I know it's going to happen with symmetry, but I'll just ignore the fact that we found that. Put negative 4, the same thing's going to happen. I'm going to get negative. Okay. So if they ask, hey, where is this graph increasing? And we're going to do open intervals. It's increasing from negative 3.5 to 3.5. Where is this graph decreasing? Where is the original function decreasing? It's decreasing from, now we got to be careful, we're not going to say negative infinity. Our graph sort of just ends, our domain is from negative 5 to 5. Okay. And in some ways, we don't really even need the arrows. You know, the arrows kind of indicate that we're investigating things that go off to infinity, and in this case, we don't need that. So there it is. So it's decreasing, going down from negative 5, and we'll use open intervals, to negative 3.5, comma, and then it's also decreasing from 3.5 to 5. So there's the increasing, decreasing. And also, something that we can get from that number line is the fact that 3.5 and negative 3.5 are going to be local extrema. Okay? So let's take a look at local max. Which one is the local max? Well, where does it go up and then down? It goes up and then down at 3.5, comma something. And the local min, that's where it goes down and then up, is at negative 3.5. Okay, how do I find those y values again? I find those y values, let's kind of move this over here, by putting, make sure we're clear with the camera. It does look pretty clear. Put those y values, to get the y values, I'm going to put 3.5 into the original function. Now, I would do this in the calculator. I would not do this in my head, because I'd have to go 3.5 squared, 25 minus that, take the square root, multiply that by 3.5, and I got an approximate, these are approximations, I got 12.5 for my approximation for how high that thing goes for the local max, and then the other one is going to be negative 12.5. So there's my local max and my local min. Now what do I have to do? What I have to do is find candidates for inflection points. So I'm going to go over here now, and to find my candidates for inflection points, I set the second derivative equal to 0. The ones from the bottom, you know, like if I set the bottom equal to 0 again, to find out where the second derivative is undefined, I'm going to get x equals plus or minus 5, which are not IP candidates. Okay, because they're right at the ends, and as we saw right there. So I'm going to go ahead and set the top equal to 0. When I set the top equal to 0, I think I can do that right here, but I'm not sure this is going to work out in terms of space. Set that equal to 0. I get x equals 0, so that happens to be a candidate. And let's just do this one right here. This is 2x squared minus 75 equals 0. 2x squared equals 75. X squared equals 75 over 2. And so what I'm getting here, 75 over 2 is quite a big number. 37.5, so that's what this is. This is 37.5. The square root of that, let's see what 37.5 happens to be 6.1. So I mean, this is going to give me plus or minus about 6.1. Now, the reason those cannot be candidates for the inflection points is because 6.1 and negative 6.1 are outside the domain. So these are not candidates as well. The only one that wins in terms of being a candidate is x equals 0. So now, what are we going to do? We're going to go ahead and say the inflection point candidate happens, kind of like we had critical numbers, the inflection point candidate happens to be 0. So what I'm going to do is I'm going to go ahead and put the inflection point on a number line. Here is negative 5 to 5, and here's 0. And I have two regions to check for concavity. This right here is the second derivative. I'm going to go ahead and plug maybe 1 into the second derivative. And when I plug 1 into the second derivative, I get positive, negative, positive. So I'm plugging 1 into the second derivative, I believe. So on the bottom, it's going to be positive, and that is negative. So it's going to be a negative. And when I plug, let's see, negative 1 into the second derivative, I end up getting a negative there. That's going to be negative and positive on the bottom. So negative times negative over a positive is a positive. And so I end up getting something like that. So this tells me the concavity, concave up, concave down, and this IP candidate actually wins the election. He is an inflection point. So let's write up some more information. The more information here would be concave up. So we'll do the open interval where it's concave up. That would be from negative 5 to 0. Concave down is from, that's where the negatives are, 0 to 5. And the inflection point, IP, is going to be 0. And then we go to the original function. Man, am I losing it here? Here's the original function right here. And I actually put 0 into the original function. I end up getting 0 times the square root of 25. I think I remember doing that. The inflection point is at 0, 0. That is the Y-intercept, the X-intercept. So now we got to put this all together and see what we end up getting. Let's put it all together. Another piece of paper, please. And so I'm going to try to put both of these number lines kind of on one number line. Let's see what we have here. So this is what we're looking at. We're going from negative 5 to 5. We have negative 3.5, 3.5, and then here is 0. Okay, so let's look at the increasing, decreasing using red and blue. It is decreasing. no, let's do increasing with the blue. It's increasing between negative 3.5 and 3.5, so I'll make this blue. And it is decreasing everywhere else, so it's going down there and right there. Now let's take a look at this chart right here. Whoa, we did pretty good at making it the same length there. So decreasing concave up looks like this. Increasing concave up looks like this. Decreasing, no, sorry, we're still increasing there, so the blue is increasing concave down, looks like this. And then this right here is decreasing concave down, looks like that. And you can actually see there's a local min there, which we got, and a local max there. You can kind of see that right there, and there's going to be an inflection point there. So let's go ahead and try to do this graph here. We have the graph there, and our graph is going to stay between negative 5, you know, it's not going to be perfect the way I do this, and 5. I'm going to have a local max at 3.5, 12.5. So my local max is 3.5, 12.5. See if we can, let's see, 3.5. So let's just put it right here. My scaling on my y-axis is different than the scaling on the x-axis. And then my local min, so, you know, I mean right here, so if you're kind of concerned about that. I just didn't have enough room here. Local maxes, so this is 12.5 on the y-axis. And then I have another one down here. Let's see, negative 3.5. It's going to be negative 12.5. And so I have that right here. That's the local min. The inflection point is at 0, 0. My X-Intercepts happen to be negative 5, 5, and 0. So let's go ahead and see if we can do this problem here. So this is negative 12.5. This right here is a local, let's label it. This is negative 3.5, negative 12.5. This is a local min, and this is 3.5 comma 12.5, which is a local max. This right here is an inflection point, so it's going to be concave up from negative 5 to 0, and then there's a min, so we're going to go like this. And then concave down from 0 to 5, and then we're going to follow this, and this is a max. And there's the inflection point. It works like an inflection point, and it goes like this, and it stops right there. And so this right here is an X-intercept. This right here is an X-intercept. This guy is X-intercept, Y-intercept, and also inflection point right there at 0, 0. And that completes our problem. I know there's a lot of stuff in these problems. Let's go ahead and consider one more thing before we end section 4.5. And I know we're coming up to an hour and 19 minutes. So if you're doing the bare minimum, you really don't have to look at this, but you know, if you remember something like this in pre-calculus or whatever you're interested in this, you're not going to have to worry about this in your homework. But this is a problem. It says f of x equals x over x minus 1 quantity squared. And now we have the way, you know, so we see a dot up here, and we know there's a break in the horizontal asymptote, and we kind of figure that it's going, you know, the graph is going to go up here and come around here, and then we figured the graph is going to come up here and break through the wall, and then there's going to be a minimum, and then it's going to go back along the wall. Now, because we know calculus, we're able to find the minimum over here, and we're not only able to find the minimum, but we're also able to find the inflection point, because this is going to be concave up, and then it's going to be concave down. So once again, this is a problem you don't have to worry about, but for those of you who want to find the local mins and maxes and the inflection points, go ahead and do it. Pause the video, and then when you unpause it, I'm going to just write out, I'm not going to do all the work on this, but I'll write out some important things. Okay, so when I took the first derivative, I'm not going to have you suffer through that again, because was I messing up on the other one? Yes, I was. I got negative x minus 1 all over x minus 1 cubed. And when I took the second derivative, I ended up getting 2 times x plus 2 on the top, and on the bottom I got x minus 1 to the 4th. Okay, I found out when I did this, in terms of local max, there was none. And the local min, so I mean, I'm not showing you all the work, but this is just for the people who paused and they wanted to do this on their own. I ended up getting negative 1, negative 1/4. And you actually have that point right there, do you see? And so that's the one I have graphed there. That is the local min. So this graph is going to come down like this, and then it's going to start coming back up. Now, if you were wondering about the inflection point happens to be at negative 2, negative 2/9. Okay, so these are some things I didn't show, the increasing, decreasing, or the concavity, but the inflection point, it changes inflection right about there, and now it goes from, here's the inflection point right here, it goes from concave down to concave up, and then your graph goes like this. And this is something you don't have to worry, whoops, missed that point. Just make the point bigger. So that's a rule for math teachers and math majors. You miss the point, you make the point bigger, and then no one will even know. Look, looking at that, hopefully there's no suspicions. And you could actually, use this in concavity thing, increasing, decreasing, local mins and maxes and inflection points, to analyze graphs that are more complicated. I did not like the rational functions that they gave us for odd numbers in the homework, so that's why I did not assign the rational functions. So in your homework, once again, as a reminder, that you're only going to encounter polynomials, which we did a polynomial, and the second part would be root functions, which we did a root function. So stay strong, and I will see you guys next time.